Okay, so welcome back. Let's remember where we are and figure out where we're going from there. So we have this notion of differential privacy that we've encountered. It's sort of the stability notion of computations. In the last lecture, we saw that this stability notion has some nice mathematical properties that potentially make it appealing. And we saw our first differentially private algorithm, this randomized response algorithm, which just said that individuals can add noise to their data, and that we just looked at the very simple bit flipping version of this, basically. We saw that that's a way of achieving differential privacy. And then after that, I hinted, but we didn't quite really get into the details of what if we want to hand our data over to a central curator and have that curator compute some function with a numeric value or with a numeric vector value and add some noise to it. How can the central curator guarantee differential privacy in these types of settings? So I want to return to that algorithm. So I'm going to skip into that. So on the way, we encounter this notion of the sensitivity of a function as being sort of a key concept here. And again, just to remind you, what's the sensitivity of a function that you wanted to compute on data? It's how much can the value of that function change as a result of moving just between neighboring databases, again, that differ by the addition or removal of a single person, okay? And so we realize this is exactly what we need to hide. And so not super surprisingly, this ends up being part of what determines how much noise we need to add in order to get our differential privacy guarantee. So I'm going to skip us back to that noise distribution that we saw last time towards the end, and you did not get a chance to absorb. Let's try to make a little bit more sense of it. So this Laplace distribution, as I was saying before, is this sort of exponentials that ran into each other. And I think the best way to get some intuition for what's going on with the Laplace distribution is to start to use it for things. But these are sort of the basic properties that you want to know about it. What's the probability density function? For the Laplace function, it has this exponential form with this b parameter. And let's think about what does this b do for us. So as the b gets bigger, the noise gets flatter, okay? So what does that mean from sort of we're adding this noise to an answer? Is that more privacy, less privacy? Flatter noises? I'm very patient.
In the chat, they say more.
More, okay. Oh, I'm very patient, but I'm not looking at the chat because I just can't handle all those windows. Thank you, okay. I'm patient for the wrong reasons. Okay, so yeah. So as you add you spread the value out more, that gives more privacy, right? But it gives you less accuracy. And what we're gonna see is that in order to achieve differential privacy, one thing that we can do is we can add Laplace distributed noise where that b parameter is gonna depend both on the epsilon, the level of privacy that we wanna guarantee, and on the sensitivity of the function that we're computing, okay? Which makes a lot of sense given everything we've seen so far. So the other thing that you want to keep in mind, this property of the Laplace distribution that's going to be really useful for us is this way of thinking about how much, oh, my pencil is not being so responsive. Oh, I did something terrible, didn't I? Hopefully I can get that back. Now you see the black screen again, don't you? It's terrible. Let me get to your screen back. Sorry about that. I killed my whiteboard. I'm trying to fix my pencil. Yes, it's back. Okay, so this property at the bottom that I wanted to highlight is this something that tells you sort of with high probability, the Laplace noise isn't too much more than blah. Okay. And the fact that we have this sort of like bounding of the tails kind of thing that we can do about the Laplace distribution is going to be useful for us in lots of ways for a reason about what it does. Okay, so this is the thing that I sort of flashed at you at the end last time. This is a statement that says if I'm computing a function on a database where the thing that comes out is a number or a vector of numbers, but ignore the vector of numbers things. That's just sort of icing on the cake. Just, a number. What I can do is I can add Laplace distributed noise, and the parameter for the Laplace distribution, just like we were predicting, is going to depend on the sensitivity of the function, and it's going to depend on the epsilon guarantee. Let's do a sanity check and make sure that those are going in the right directions. So remember, B bigger is flatter Laplace, that thing we just said. So sensitivity bigger is flatter Laplace. Does that make sense? Is that the right direction? Yeah? Okay. And epsilon bigger is tighter Laplace. Does that go in the right direction? So, okay, epsilon bigger is worse privacy and tighter Laplace. Okay, so they're going in the right directions at least. Good to do the sanity check, right? Okay. So now what we want to do is we want to actually get ourselves a proof that this thing is in fact differentially private. Okay, so the claim is the Laplace mechanism preserves epsilon comma 0 differential privacy. Let me get myself some space to work on that. Okay, so you guys have already seen a couple of proofs of differential privacy. You're starting to get in the habit here. We're going to do like small style changes is how we approach the proof, but the basic idea is going to be exactly the same thing that you've seen so far. You should be starting to get kind of comfortable with this thing. So how do we do the proof? Okay, what do we need? Well, we need to imagine a pair of neighboring databases, right? So let X and Y be neighboring databases. And we're going to consider some function because we want to show that the Laplace mechanism that adds noise that depends on the sensitivity of the function at hand. So we need to sort of name this function. And maybe just for convenience, let me write P sub X for the probability density function of ML, this Laplace mechanism on the input database X, this function that we're trying to compute, and some epsilon parameter. And similarly, I'll write P sub Y for the probability density function of ML, except operating on database Y, okay? Again, tell me when my handwriting gets so atrocious that you can't handle it. And now what do I need? I need one more thing to talk about. I need a subset of the outcome space, remember? It's an epsilon 0 differential privacy proof. Maybe you've done this part of the homework already, so you know that I can just focus on a single outcome in the outcome space. So I'm going to consider some outcome. And what do I need to do? Let's do the ratios version of it, okay? So I need to reason about the probability that the mechanism, given X is the input, is going to give Z versus the probability that it's going to give Z if Y was the input, right? Okay, so P sub X of Z versus P sub Y of Z, okay? So once again, we don't know a lot. We don't have that many tools. What can we do here? Well, what's the probability that we get this particular vector Z? Well, it's the probability that we get the first element of Z times the probability we get the second element times the probability we get the third element, so on and so forth. So we can just write this product up here. Okay. But what's the probability that we get a particular element I of this vector Z as our output when we run this mechanism on, say, the input X? Well, something, but we don't really remember what that distribution was. So let's go back and remember what the Laplace distribution was. So we somehow take the true value and we add, so we take the true value, we add some Laplace noise to it, where that Laplace noise has this particular B parameter. And what was the distribution of the Laplace noise? Let's try to remind ourselves. Oh yeah, it looked like this. It had this exponential form, okay? So we're gonna take this and we're going to just basically copy that right down onto our slides. Okay, so that's what we're doing. Let me get ourselves back down to here. So this is going to be exactly that. We're going to start at the value that the function actually takes. And the probability that we instead answer with z sub I is parameterized by the distance between those two things, and this sensitivity and this epsilon, okay? And this is just the definition of our mechanism. We're just feeding it right in there, okay? So, and then similarly, exp of, and then we have to run f on y, see how far that is from z sub I, feed in that sensitivity. Okay. What can we do? We don't have a lot of options here, but we have some, things we can at least clean up and reorganize. So let's do it. Okay, so let me bring some stuff down from the denominator up to the numerator. So I have this distance here between f sub y, I. So I took in the negation there to try to neaten things up a little bit. And this f on x. Tell me if I'm messing this up. You have to catch me if I do. Look okay so far? Yeah, you approve? All right. So then, now what? This thing should give you an idea. What can I do? Got sort of a distance to a thing, another distance to that thing. What do you do when you see that? It's too obvious you're not willing to say triangle inequality? Okay, I believe you were thinking it. So we want to sort of apply a triangle inequality here. And so what are we going to be able to say? That's this product. This distance between f applied on x, f applied on y, and this is starting to look really good. Okay. What can I do now? So I have this sort of e to the epsilon over sensitivity of f. And I have this, I'm multiplying together a bunch of terms that have this going on in them. And they also each have this distance between the f of x in the ith element versus the f of y on the ith element. So that I can just rewrite this as giving me the L1 distance between these things here. Okay. And now what can I say? I don't know very many things, but what's one thing that I do know about this? How much can f change when moving between neighboring databases? The sensitivity. That's just what the sensitivity is. So boom, boom, sensitivity cancels out, and we have this bound. Are we done? What's the check that I'm asking you to do here? I'm asking, was there anything special or sort of symmetry breaking about which was x and which was y? No, we're good. This goes in both directions. So we're done. Okay, so we know that the Laplace mechanism that adds this Laplace noise with the parameter that depends on the sensitivity and depends on the epsilon that we want to obtain gives us the guarantee of epsilon differential privacy. So what this tells us is now we have a tool where we can go around answering queries that have numeric values or sequences of queries that have numeric values. And we know how to do that with differential privacy. And this is, already pretty cool. It's already a pretty powerful thing. What we didn't do is we didn't say how good this is. So it's never satisfying to just prove that something is differentially private without thinking a little bit about, what is the consequence for accuracy. I didn't really do that explicitly in the context of the randomized response algorithm. And so for that, I apologize. But here, let's think a little bit. What would it mean to give an accuracy statement for the Laplace mechanism? Well, you can imagine a number of possible types of statements, but one natural thing to do would be to say something like, except with high probability, the Laplace mechanism doesn't add too much error to the answer. And how would we be able to do that? We don't actually need to do any proof for that at all. You get that immediately from this property of the Laplace noise. Except with some small probability, it doesn't add too much noise. So that's your accuracy theorem right there. You just instantiate that with the parameter that goes in your Laplace distribution. So that's your accuracy theorem, but you should always demand an accuracy theorem to go with every privacy theorem. Okay, so we know that it's, accuracy degrades naturally as you demand more privacy. Now let's think a little bit about what the consequences are now that we have this mechanism. So one thing we can do is that if we have some queries that we know have not very big sensitivity, we can go around and answer them with guarantees of differential privacy. If we have queries that we know are really sensitive, we don't have a really good tool because we're going to add a huge amount of noise. But if the sensitivity is low, for example, we have these counting queries that ask how many people, you notice before I normalized it, and this time I didn't normalize it, how many people have a certain property in this database, like how many people are women or how many people are female computer scientists, then the sensitivity is 1. So we can add noise that scales like Laplace of 1 over epsilon. So that's not too bad. We also can handle these vector valued queries of some dimension d, and then we can apply our sort of naive composition arguments to show that we can add noise that scales with d in each component of the output. And again, it's going to have to depend on the epsilon and the sensitivity. The important thing is, this sort of d pops up in there, and that makes sense. We saw before that privacy guarantees add up. So if you want to answer a sequence of queries, you're going to have to sort of split your privacy budget among those queries. And this is one way to do it. You could also split your privacy budget unevenly. There's no law that says I have to give the same privacy guarantee to each of the queries that I answer. And so you might consider in some settings, maybe it's worth answering some queries more accurately and other queries less accurately, or some more privately and others less privately. Depends what you're trying to optimize. So you have this option. So that's all nice. So we can answer, sequences of queries. We can divide up our privacy budget to do that. Here is one particular sequence of queries where we can start to get a little bit more clever. So what if what you want to do is answer a histogram query? What do I mean by a histogram query? I mean, you answer how many people are in each of a bunch of different disjoint bins. Like how many people in your data set are between the ages of 0 and 4, how many between the ages of 5 and 9, how many between the ages of 10 and 14, so on and so forth. Okay, so these are disjoint bins. So one thing we could do is we could count the number of bins and scale the noise accordingly, right? Because it's just a bunch of count queries. But actually, it turns out we can do better than that. We can add noise that doesn't scale with the number of bins. Why? Any ideas?
So is it because of the L1 norm changing only?
Yeah, so we can observe that if we treat all of these queries as a single vector valued query, how much can that vector change if we change the database by adding or removing one person? Well, how many entries in the vector can change? 1. And how much can it change by? 1. So the L1 change in this entire vector valued query is bounded by 1. So we used, in this sense, the fact that these were not totally unrelated queries, but actually these were queries that had sort of an intimate relationship to one another. And we use that fact to get a much better result. And this looks sort of wildly cool the first time you see it. Well, I can answer, arbitrarily fine histograms, and the amount of noise I need to add doesn't depend on the number of bins. That sounds like too good to be true. Why is it not too good to be true? What's hiding there? It sounds like magic. I can get sort of arbitrarily good histograms, right? You just make them finer and finer and finer.
Each histogram needs to be disjoint, right? You can't
the bins have to be disjoint. Yeah, that was key here because we needed each person to show up in at most one bin. Yeah, that's a really important point. Yeah. But why can't I just make my histogram finer and finer and finer and get a more and more precise picture of the data distribution?
At some point, it becomes useless. Only one person would be per each bin, and adding noise would just destroy the.
Exactly. So that's why this isn't just total black magic, because as you make the bins finer and finer and finer, there are fewer people in each bin. And so the answers eventually become meaningless because the noise just, is more than the signal. So there's some dance to be done to figure out sort of how finely you want to bin things, so you get sort of something that's useful out of it. So there's no free lunch here. Okay, so that's satisfying. That makes a lot of sense. Okay. Suppose the problem that we wanted to solve is we wanted to determine, say, the most commonly liked Facebook page subject to differential privacy. How could we solve that problem? So there's, I don't even know how many pages on Facebook, a whole lot of them. An individual could I don't know, all of them, I guess. Probably not technically, but okay, I don't know how to put a bound on how many times somebody can hit the like button. So how could I do this? So I could try to give a differentially private count of the number of likes that each page got. But if I wanted to hide the presence or absence of any one individual from the database, then I would no longer have this nice small L1 change in all of these counts, because one person could change the number of likes of every single page. They can only change it by one. We only let you like one time, but you can change every single page. And so that's potentially, if you're really patient and you keep clicking that button, a lot of change in the L1 distance. So what can we do to do something like this? Any ideas?
Some kind of GP ranking?
Yeah, we want to sort of get at the fact that what we want is somehow, we don't actually care about the counts of every single page. We just want to know which is the most liked page, which is the biggest. And somehow that feels like it's less information. It should be less revealing. And like you said, it's kind of like we're just trying to get at a ranking or even something simpler than a ranking. So how can we kind of get at the fact that that has less information contained in it? Can we do something clever here? So the idea here is the following. It's called the report NoisyMax algorithm. What we're going to do is we're going to take all the counts and we're going to add noise, but we're not going to scale that noise with the number of options. And then we're just going to report the index of the largest noised query. So we're not going to return all of the values of all of the noise queries. We're just going to say, this was the most liked page. So the algorithm makes sense? Yeah, okay. So now the claim is that this is actually epsilon zero differentially private. So even though one person could actually change all of the counts, and we only added noise that looks like it should hide a change of one in one of the counts, somehow we're going to get a privacy guarantee here. Okay? Questions before we go to try to prove this? Okay.
So there is no dependency on M here at all?
That is exactly the point of skepticism that I was hoping someone is going to get to. I'm glad you got there. So I'm not going to answer that yet. Hold that skepticism and sort of that this doesn't seem right. Hold that thought until we get to the end of the privacy proof, and then see if you can answer your own question at that point, okay? But you're completely right to have an uncomfortable feeling in your stomach. Like, where is that M? It ought to be there somewhere. So keep that in mind. Hold it, and we'll come back to it. Okay, so, all right. So the claim is that report NoisyMax is epsilon comma 0 differentially private. Before we analyze the algorithm, just I want to make sure that everybody's comfortable with what the algorithm is. It's very, very simple. We have this vector of counts, and we're just going to add Laplace distributed noise to each of them. But the parameter for the Laplace distribution is just going to be this 1 over epsilon. Okay. All right. And the claim is that somehow this is going to be epsilon comma 0 differentially private. Okay. You guys know how to do a proof of differential privacy. I'm going to, once again, slight tweak in how I presented, but you've got the basic idea here. So I'm going to fix two databases. One, which I'll call, I guess in the book, I'll try to follow the book. The book, I think, calls it D. And the other one is D prime. They differ in the addition of one person to the database. And again, that person is allowed to like all the pages. And we're going to write C and C prime for the vectors of counts under these two databases of people. Okay. So now we're going to give fancy names to two really very simple properties here. One is a monotonicity property, which just says that when you add somebody to your database, the counts only go up. You can't like anti-like a page. And the other property that we're going to notice is what we'll call Lipschitz property. It's again a very simple observation. It just says you can only increase the counts of the likes by at most 1. Okay, so when I move from the database without A to the database with A, counts only went up, and A only increased counts by at most 1. That's all I just said. Okay, so now what we're going to do is we're going to consider some possible output of the algorithm. That's the thing we always do when we think about differential privacy. Again, it's epsilon comma 0 differential privacy, so I don't have to look at a subset of the output space. I can focus on a single output. What is an output? Well, an output is an index. This one's the most popular page index. So I'm going to fix some index. Okay. And this is the output of the algorithm. And now I'm going to do something a little tricky and a little clever. I'm going to do my analysis actually fixing the noise draw of the Laplace noise on all of the entries of the vector except for the ith one. Okay? And I'm going to do sort of, you can think of it as I do the analysis for each possible setting of the draws of the noise for everybody except the ith entry of the vector. And then the only randomness I'm going to carry around in my analysis is the randomness from that ith draw of Laplace noise. Okay, so I'm going to fix this noise for everybody else. And then we'll argue for each of these draws. Okay, now I'm going to give myself a little bit of notation. So I'm going to define R star to be the smallest amount of noise that I would have needed to add to the ith entry, given all the other noise that I already fixed for the other entries, and given that the input database was D, in order for I to win. Okay, it's actually easier in math than in words, so let me write the math and then I'll say the words again. So it's the min amount of noise that I could add to this, the count of entry I under database D, such that it would win, given the noise that I had for everybody else. Okay, so this is smallest. Let me write this smallest. Okay, under D. Make sense? Okay. So now I'm going to reason about the things that I know how to reason about. As usual, I don't know a lot, so there aren't a lot of options here to do the proof. So for all entries not equal to I, well, what do I know? Okay, well, I know that C sub I plus this R star is bigger than C sub j plus Rj. And I have these two properties, this monotonicity and Lipschitz properties. They tell me something about how I can relate, you know, CIs and CJs, sorry, how I can relate counts when I move from the database with without A to the database with A and vice versa. So let me just plug them in. What do I know? So this is, what can I write that's bigger than this? Well, I know how to write, you know, based on this, something that's bigger. So let me write it. 1 plus Ci prime plus R star. And what do I know how to write that's smaller than this? Well, over here, I have some lesson on how to write things that are smaller. So let me do it. C sub j prime plus Rj. Okay. So now I have that, you know, this is bigger than that. So what does that tell me? Let me rewrite that. So I can rewrite this as Ci prime plus R star plus 1 exceeds Cj plus, oh, sorry, Cj prime plus Rj. Okay, so what does that mean? It means that the ith count on the bigger database, oh, sorry, on the smaller database, so the D prime is a smaller database, the ith count on the smaller database plus this, so slightly more noise than I needed in order for I to win before, makes I win. Okay, so this amount of noise is sufficient for I to win under database D prime. So let me write that. So if Ri exceeds R star plus 1, I will win under D prime. Again, this is fixing the rest of the noise here. Okay, so what can I do with that? So what's the probability that my algorithm, this very simple algorithm, that again, what does it do? It adds independent Laplace noise to each of the entries, parameterized by 1 over epsilon, and then it says, this was the biggest noisy entry. Okay, what's the probability that algorithm answers I, given that the input database was D prime and the noise was this fixed noise that I've been carrying around? Well, what do I know? I know that it's at least from this proof that I just did. Let me give myself some more room. It's at least the probability that this R sub I exceeds 1 plus R star. And what do I know about that? Well, I know how the Laplace distribution is behaved, right? And in particular, one of the nice properties of the Laplace distribution is that's bounded by e to the minus epsilon times probability that Ri exceeds R star. And what do I know about the probability that Ri exceeds R star? Well, I have a name for that. That's the probability that I wins under database D. So I've related the probability that I give you an answer of I under database D prime to the probability that I give you that answer under database D. Am I done? No. Why not? What is the check that I always want you to do at this point in the proof? Was it symmetric? No. Why not?
The database have different sizes.
Yeah, the databases have different sizes, and I started with a specific one of them here. I knew which one was bigger, and I made use of that in the way that I reasoned about things. So maybe I'm in trouble. I have to check the other direction. Now, if you're incredibly insightful, maybe you see right through the next direction and it doesn't go all that differently from this direction. You see that it all works out. But let's be careful. Let's do the other direction, maybe a little faster than we did this one, just to sort of see that it all works out. Okay. Questions, though, before I force you through this other direction? Okay. So other direction. And that's why I was being so annoying. And I was asking you at the end of the proof, are you done? Because you really have to check. So I'm going to define this R star to be the smallest amount of noise such that I wins under D prime. This version of the proof is going to look remarkably like what we just did. In fact, to the extent where there's a decent chance that I will write something backwards, so you should check for it. This is the smallest noise such that I wins under D prime. Now, what do I want to say? I want to say for all j not equal to I, what do I know? So I know that Ci prime plus R star exceeds Cj prime plus Rj. Okay, how can I reason about these quantities? Well, okay, they're no longer on the screen, but I have my monotonicity and my Lipschitz properties, and I'm just going to apply them. So I have that Ci plus 1 plus R star is here, and I have that Cj plus Rj is over here. And so what can I say? Oh, sorry, I skipped a step in a bad way. All right, let me do that slowly. Sorry about that. Okay, so what do I know here? I know how to reason about, and I actually really should bring these down so you can see them, because that wasn't fair at all. Here we go. Let me copy this so we can see this. That was not at all fair. Here we go. Okay, so here are our properties. At least we can see them now. So what can I do? I skipped a step, and you can see, so you couldn't see it. What I want to do is I want to say that something is bigger than this. How can I do that? Well, I can go, straight to Ci being bigger. I'm going to eventually want to have this, +1 running around. So one thing that I can do is I can add 1 to both sides of this. And I did that at the same time that I did everything else. So it was a little confusing. So let me add 1 to both sides. And then I'll do the step that I did before, which maybe you believe me, but you didn't have good reason to. And now I can do this step. Okay, so now, there we go. That was right this time. Okay, so now what I know is if R sub I exceed this R star plus 1, I will be the output on database D, okay? And so again, I can do the same sort of reasoning. So the probability that I get I under D, given the noise, is greater than or equal to the probability that Ri exceeds this amount that I just calculated. And now I use my fact about the Laplace noise to say, well, that's related to the probability that that Ri exceeds actually R star, and that is equal to e to the minus epsilon times the probability that I answer I under D prime. Okay, now am I done? Yes, all right, I agree with you. Okay, it turns out you can also extend this proof to release the maximum noisy count, not just the index, and even with no further loss of privacy. So now what I'd like you to do is I'd like you guys to go out into breakout rooms for just 2 minutes, and I'd like you to say, what about an accuracy proof? So we did a privacy proof. You're never supposed to be satisfied unless that comes with an accuracy proof. I'm not going to ask you to do the accuracy proof in the breakout rooms. I'd like you to figure out what the accuracy claim should even be. What should an accuracy theorem for this algorithm look like? Does the question make sense? Okay, somebody who has the powers of breakout rooms, can you send everybody out into groups of 5 or so?
Yeah, sure.
Awesome, let's do it. Welcome back. Any progress on what you might hope for an accuracy guarantee for something like this?
Yeah, at first, me and Kartik and I can remember the name of the other person. We were thinking like, oh, maybe with high probability the maximum doesn't change, but this didn't feel quite right. Like just saying with high probability, like just a binary thing wasn't like, didn't sound nice. But I guess it depends on the distance between the true maximum and the second guy, and like the higher the difference, the less likely it is to change.
Yeah. Okay. So all of that's really, really good intuition. Yeah. So at first you want to say, oh, like with high probability, I get the, the true max. And then you realize, well, hold on, it depends how isolated the true max is from everything else. So maybe what you want to do is instead say something like, with high probability, we output an index whose true count isn't more than alpha off from the true max. And we don't have time to go through this, but actually this is something you can do in 3 or 4 minutes on your own at home, is you can reason about this basically by saying, okay, what would it take for me to accidentally output something that's a really bad answer here? Something whose true value is really far off from the true max. Well, one or both of those noises would have to be pretty big in order for that to happen. The true max could get knocked down, or the really bad thing could get knocked up, or it could get knocked down a little, and this could get knocked up just enough that it cross, something like that. And so it's not the maybe cleanest way. Or, okay, it's very clean. It's maybe not the most precise way to analyze this, but one simple way to analyze this is just check, can I bound the probability that any of the counts go up by alpha over 2, and the probability that the true max goes down by alpha over 2. And as long as we don't have anybody changing by more than alpha over 2, we're never going to output something that is more than alpha off from the true max. Does that make sense? So then all you have to do is you need to bound the probability that your Laplace noise can be off on anybody by more than alpha over 2. And that's exactly what we know how to do with the Laplace noise. We know how to bound the probability that it exceeds something. And now we just have a bunch of independent draws. So that's a pretty straightforward accuracy analysis you can do for this. But the reason I sent you out into groups is to see that sometimes it's not immediately obvious what accuracy theorem you want to prove, and you have to think a little bit about what accuracy is going to mean and what's going to be feasible in the context that you're looking at. Okay, so that's it for today. To remind you where we are, we've sort of gotten to see a few more sort of pieces of the toolkit. We know how to add this Laplace noise. We've seen some more proofs of privacy. We saw this sort of slightly more clever things about histograms and about report NoisyMax. We only have one more lecture together. And boy, is there a lot of stuff that I would love to cover. But what I hope to do with that time is give you some intuition for how we can cleverly answer potentially far, far more queries than we've been able to answer so far, and talk a little bit about how you start to take this toolkit to build up other more sophisticated differentially private algorithms. So that's the plan.